alternative current. In this chapter, we just want to understand what the alternative current is. And we want to find the root mean square value and the average value of the alternative current. And then later on, we just want to study about circuits consisting of resistor, inductors, and capacitors. And also, we can study about the circuit consisting of the three loads here, but then connected in the series, in the parallel, and then in the mixed combination as well. We need a tool. This tool is called the phasor diagram. We can use the phasor diagram to solve for the reactance and the impedance, and also the voltage amplitude, the current amplitude, and the phase of the circuit as well. And then finally, for this chapter, we just want to study about the resonance of the RLC circuits in the series combinations. So then, the first topic that we just want to talk about is the alternative current, stand for this AC, right? The alternative, the current. But then before that, let's talk about the DC current first. So you have learned already from the chapter about the direct current, right? For example, if we have the DC source here, and then we just connect the source to the resistor and with the ammeter, so then we can measure the current through the resistor to be the line, a straight line. Okay, so we can say that this current is constant. But then on the other hand, if we have the AC source, so this will be the symbol of the AC source. So it just looks like the psi function. And we connect this AC source with resistor and the ammeter. So then if we look at the graph between the current and then the times t, right? So you can see that the current will just oscillating up and down, from this graph. So if we have the psi function, so that's why this function we just call it as the sinusoidal function here. So now for the positive current, for this part, it means that the current will just flow in one direction, and this negative part, it means that the current will just flow in another direction. Okay, so that's be the meaning of the positive value and the negative value of the current. So in this case, it means that the current can flow forwards and the backward, forwards and backwards, etc. We can have the maximum value of the current, so it's called the I naught. So now this I naught here, this I naught here, it's just called the current amplitude. It's called the current amplitude, which is the maximum value of the current. And also, because the current here is the psi function, so it means that we must have a period. So if you remember what is the period is the time for one revolution, right? It means that the period t here is the time that the current just go in the forward direction and then backward direction and then come to its original value, which is 0 in this case. Okay, so that's called the period. If we know the period, we can find the frequency and the angular frequency as well. So now for the angular frequency, we use the symbol as the omega. So we can have that the omega equal to the 2 pi and then over the period equal to the 2 pi times the frequency. So I guess that you have seen this many times already. So we'll go quite a little bit faster. So we know that in Thailand, right? In Thailand, the frequency is equal to what? Equal to 50 Hertz. Okay, in Thailand, the frequency equal to the 50 Hertz. It means that in 1 second, the current will oscillate 50 times. So it just go back and forth 50 times in 1 second. So this will be the frequency of the electric current in Thailand. So when we talk about the objective current, we don't need to have only the sinusoidal function, but we can have the square function as well, or we can have the triangle function, as you can see from this picture, right? So it means that we will have the maximum value of the current, which is called the current amplitude, as I mentioned already. So this as well is going to be the maximum value of the current, and we also have the period of the current. So don't forget that the period is going to be the time for one revolution. Okay. But then in this chapter, we just want to consider only on the sinusoidal function here. So that's going to be the main objective of this chapter. But then what happens if we have the square function and the triangle function? So that's still quite simple, because the square function and the triangle function is just going to be the superposition of the sinusoidal functions with a different amplitudes or the frequency. Okay, but we just don't want to talk about this thing. Okay, so now let's come back to the sinusoidal function. So let's just write down the current as a psi function. So then we can have that the current here equal to the I naught, right? And then times the psi omega t. So don't forget that the I naught here just represents the current amplitude, the maximum value of the current, and the omega just represents the angular frequency, which have unit as the radian per second here. Okay. But then on the other hand, if we just want to talk about the potential difference across a load, so this load, it just means that it can be resistor, capacitor, inductor, or it can be the combination between resistor and capacitor, resistor and inductor, and etc. Okay, so that's called the load here. So we use the symbol delta V, right, for the potential difference equal to delta V naught again. So this delta V naught, it will represent the maximum value of the potential difference. Okay, so it's just called the voltage amplitude, or it's just called the voltage amplitude here. Okay, but one thing which is different from the current is that I have this one add up to the omega t. So this is called the phase difference between the current I and the potential difference across a load. Okay, it's called the phase difference between the current and the potential difference. The phase difference here, okay, if you have the unit as the radian as usual, or sometimes we can just find the unit to be the degree as well. Okay, so let's look at this graph. So this graph, the horizontal axis is the time, and the vertical axis can be the delta V and the current I. So let's consider the current I first. So we have the current I, right, to be the I naught, and then times psi omega t. It's just simply the psi function. So it's this curve, the black curve here. Okay, this is for the current. But now for the delta V, if we have the phase difference to be the phi, right? So it means that the graph must be shift. Maybe shift to the left or to the right. So it's be this one for the delta V. Okay. Now from this graph, okay, so I just want to mention that, I mean specifically only for this graph, you can see that the phase of delta V is leading the phase of the current. The phase of delta V, it just means this one is leading the phase of the current. So the current graph is this one. So why we say just leading? So let's look at here. Let's look at this part. Okay. So you can see that with the times equal to the 0, with the times equal to the 0, delta V graph has this value already. Okay, if it has this value already, But when you consider the current graph, it's just still 0, right? So then when the time goes by, here, so you can see that the current graph give me a sec. Okay, so when the time goes by, right, you can see that the current graph just have this value which the delta V has already, initially. Okay, so it means that the phase of delta V is leading the phase of the current I. Okay, so that's called the phase of delta V is leading the phase of the current I. Or we can say that the phase of the current I is lagging the phase of delta V. Okay, so now we have the two words that you should know, the phase leading and the phase lagging. So now from this picture, it means that the phase of delta V is leading the phase of the current, or we can say that the phase of the current is lagging the phase of delta V. Okay. One thing that I just want to mention before we go to the next topics. Okay, so let's consider these two functions here. You can see that when we talk about the amplitude of the current or the amplitude of the voltage, I use the capital letter. Okay, so I use the capital I and capital V for the amplitude. When we talk about the quantity, depending on the times t, I use the small letter. Okay, so that's why you can see that I use the small I for the current depending on the time. I use the small delta V for the potential difference depending on the time t as well. Okay, but don't forget that for the amplitude, we use the capital letter. So the one depending on the time, we use the small letter here.